Hi, Dr. Geeta Ramani. Good evening. Yeah, please confirm, friends. So, are you able to hear me and see the screen? Okay. Few people are able to hear me. Uh, okay. Majority of them are not able to hear. 50. Okay. Thank you, Lakshmi. That's strange. You should be able to. Okay. Majority of the people are now able to see. People who are not able to see. Yeah, I request you people to please reconnect. Okay, yeah. Let me begin. Good time to begin. Okay. So today's session, we are talking about Step AIC. We'll try and understand how this feature selection is done and what exactly is this Step AIC, right? So welcome to today's session. The webinar is conducted by 360 Digit MG in association with MDEC. And today's topic is Step AIC in regression analysis. Now, what is Step AIC and how do we use this? Yeah, that's basically what we are trying to understand here. So let's start. What exactly is a Step AIC? Now, before I proceed with Step AIC, discussion with Step AIC, you people should be aware of regression analysis. Now, regression analysis is part of your supervised machine learning. Supervised learning, wherein we try to do prediction. We are trying to do prediction of a variable of interest. And in order to predict this, we express the relationship between y using this function. Now, under supervised learning techniques, we have different approaches based on the output variable that you are trying to predict. Now, it can be numeric. That means your output variable y that you are trying to predict could be a numeric value, or it could be a non-numeric value. It can be a numeric value or it can be a non-numeric value. Right? Now, if it is numeric, then we can easily develop a mathematical equation. And the techniques that we are going to call here are regression techniques, or we also call them as prediction models. We call them as prediction models. Now, if you have non-numeric data that you have to predict, then we call these models as classification methods or classifiers. Right? And always remember the output variable is getting affected by a bunch of input variables. And we call these input variables as features or attributes or independent variables. And your y is a dependent variable, which is getting altered based on the changes that we are seeing in x. As in how x changes, we are seeing that y is also changing. So that's about the overview backdrop of your step your regression. Now, when you're trying to develop your model, a predefined mathematical equation can be used. Now we're just verifying whether the relationship can be expressed using this predefined equation. And whenever say we talk about this predefined equation, we talk about, let's imagine a two-dimensional data, and we try to define the relationship using a linear line. Now, when I say linear line, the relationship is consistent. That means if x is increasing by, say, 1 unit, then the y gets affected by, let's say, a units. It is getting affected by a units. Irrespective of what value of x you are trying to deal with, if you are altering by 1 unit, then your y gets affected by a units. Okay, that's your linear regression condition. If this consistency is there, then the data points will fall exactly on that straight line. And in such a case, yeah, it's very easy to define a mathematical relationship using y is equals to mx plus c. It's a straight line equation. We all know about this equation. We have been studying that in our primary classes as well, right? School days. Now, ideally, you'll not have this kind of a very simple straight line equations. In real-time world, the relationship between x and y would vary a little. It will not be perfect line like this. So it will be something like this. And regression analysis is about identifying the best fit line. Best fit line. Then you're trying to fit a line into the data. Right. Now, This is a simple example where you're talking about X and Y. But you know, Y is getting affected by a lot of variables, right? And this equation is extended to that multiple dimensions. The equation has beta naught, it's a coefficient, beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus so on and so forth. I need to write it in the same font. Based on the number of input variables that we have, we are trying to bring in those variables effect into Y. But in order to get this, there are certain conditions that we need to look at, which is called as line assumptions for regression. If you're trying to use this best fit line equation, then we have this regression condition, right, where you say line assumptions. Right? Now these line assumptions talk about the mandatory, I should say, characteristics that the data should follow to satisfy the conditions and give us the best fit line, where L is linearity. So here when we talk about linearity, we need to have Y and X having linear relationship. At the same time, we should not have X and X as linear. This is something we should not have. If you have this case, then it is called as a collinearity problem. Then I means independent. I means independent, which basically says that the errors that we are getting, right, when you are using this equation and try to develop a model, and if you get an error like this, then when we look at these errors, we should see that these errors are not affecting each other. They should be independent of each other. That's another property. If they are not independent, then we get a problem called as auto correlation. Then we have N. N means normality. Any data which is continuous in nature should have normal distribution. So errors are also continuous in nature and they should follow normal distribution properties. And the best fit line should give the average of errors as 0 always. The representative value of errors for the entire data set by explained using that equation that we are coming up should be 0. That means it should be the best fit for the entire data set considered, not for one data point. Then we have E. E means equal variance or consistent in variance. The errors that we are having should be identical. Identical. If not, then you're going to get heteroscedasticity problem. Heteroscedasticity problem. Right? These are the conditions that we need to look at when you're developing or when you're working with regression analysis. Now, when you work with all these variables, let's say you have been given 30 odd variables for a business problem where you have to predict Y. Assume. Then you cannot, right? I mean, you can. But ideally, you'll not be utilizing all the 30 columns because a lot of columns, a lot of variables there are repetitively sharing the same information for a given Y. Generally, that's the case in the real-time scenarios. We'll have 30 different variables and we have to use those 30 variables in developing this model. And before we proceed, of course, we do EDA. And as part of that EDA, we use scatter diagram. We come up with scatter plot. Then we come up with correlation values. Right? Correlation values to identify which variables are better. Right? Among all these variables, you need to decide which variables are actually relevant in considering. Maybe out of 30 variables, you found that only 20 are relevant. The other 10 are not at all relevant, so you can safely ignore them. Right? So you can safely ignore them completely. Right? So this is basically your initial EDA that you are going to do. So let me erase this. And when you are developing your linear regression with those 20 cases, let's say 20 input variables, right? One single output variable, you get that lengthy equation. Okay. Now in this equation, of course, we have to validate the model, right? I mean, we need to evaluate the output, validate the output. The coefficients that we are getting have to be significant. So in order to check that these are significant features in predicting Y, we look at their respective p-values. And these p-values, right, should have the value which is less than the standard, which is 0.05. So the p-value should be less than 0.05. If not, then these values become insignificant. Right? These values become insignificant. Remember that. Okay? Now, these insignificance might be caused by various reasons. One of the primary reasons is collinearity problem. Right? There might be collinearity problem because of which your features are becoming insignificant. And those features, those kind of features have to be eliminated. Of course, we have already checked the collinearity problem earlier and then removed it. Remove those collinear pairs. But still, the relation between the variables could be very strong, right? Which is basically making them interact with each other. Right? They are making the interaction between the input variables stronger. And because of that interaction, the influence on output is reduced. Yeah, the input, the influence on the output is becoming reduced. Right? Now, when you're trying to apply these kind of regressions, right, we are ultimately doing what? By looking at all these steps, we are selecting the features which basically give us the best result. Right? What are those features which are giving you the best results? So I'm going into a concept called as feature selection. Right? Feature selection. So among 20 different variables that you have, you need to choose the most appropriate features. Right? Now these features should give you the best equation. Okay? And one of that approach, one of the feature selection approach that we do is nothing but your step AIC. Right? We are trying to understand step AIC here. Now, step AIC is a simple parameter is a calculation, right? Your R or Python programming, they have ready-made functions. You just use those functions, and the step AIC will be calculated for each and every parameter that you are trying to capture. Okay, whatever the variable that you are capturing, right? So it captures that step AIC. Here we are talking about AIC. Step AIC means you're trying to look at the AIC value stepwise. AIC stands for Archaic Information Criterion. Criterion means plural, right? Now this AIC value, of course, standalone does not have any value, is used to verify the information loss. Loss functions are, right? Your cost functions are there, right? So you're trying to see how much information is getting lost. Because we are trying to simplify your equation with those 20 different variables. You don't need all of them, right? You try to have simple equation. So what we try to do here is every time you're generating a linear regression, it captures this AIC value. Okay, so you probably try one model with 20 variables, and then if you identify that one of the variable is not relevant, you probably remove it. So you might have 19 variables, and then again you develop a model, you get AIC, right? So these AIC values are compared, right? We are trying to look for AIC between both the models, right? And the value which is smaller, right? We consider that particular AIC, that particular model as the best model, right? And yeah, this is used for feature selection. And it is always a relatively comparative method. I mean, relative comparative method. Here you're doing the comparison here. And step AIC internally verifies the multi-collinearity problem and eliminates those values, right? So it does that internally. So it calculates the AIC for each and every model or each and every, right, calculation that we are doing, right? And then it gives us the best results, right? So we iteratively try and do that. So step AIC is a function which does this automatically. You don't have to manually try and do that, right? Now, whenever you're trying to apply this step AIC function, then for step AIC function, you are going to pass two parameters, right? This is a function. For this, you're passing two parameters, right? You develop the equation y is equals to beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth. This would become your input. And another input for this model, step AIC function, is what kind of feature selection technique you want to apply. So there are three different feature selections that we can apply. One is stepwise. It will check both forward and backward. The other one is backward elimination technique and forward selection method. So very simple logics. Let's try and understand backward, and then we'll try and understand forward. And yeah, probably we'll look into code. So these are feature selection options. So we have stepwise regression technique. So we are simply applying a model. We get the model, right? We take y and x. A single x is what we are taking, right? And we develop a model, and see what is the p-value for this coefficient that you're getting for this particular x. Now this p-value should be less, right? Now we keep adding another variable. Once we've selected, let's say, one variable, we add another variable to it. So now you'll have x1 and x2, for example. Now for these x1 and x2, two variables, we are trying to see what are the p-values again. Now because you brought in this x2, a new variable into the picture, is it affecting the relation between x1 and y? It might be correlation, right? So if there are such issues, then the p-values will become insignificant. So you can eliminate those variables. But if your p-value is not insignificant, I mean it is less than 0.05, then we keep those variables. We repeat this. For all the variables, we keep repeating this and we pick the best model. Now forward selection is just like this, right? So here in forward selection, we just keep adding the features, whereas here you can also delete. We'll consider, we keep adding the variables only which are relevant. So if once this is added, it is added. We cannot change that. We cannot remove it. Whereas here you can also remove that, play around. That's the difference. Now backward elimination is just quite opposite to what we discussed here. You simply develop the entire model. You take all the variables, whatever the list of variables you have, you take all the variables, and then we keep removing those coefficients, or we keep removing those variables which have coefficients as highest p-values. The values which are greater than 0.05, we remove them, right? We keep removing them. So this is backward elimination. One after the other, we keep removing. Let's say x1 is greater than, the beta 1 value is greater than 0.05. So we remove this. Then we redevelop the model with the rest of the variables. Again, we check. Probably coefficient 5 is having the next highest p-value. We eliminate that, right? So we keep repeating these steps by eliminating the variables and generating the models. So forward selection, which starts as y, and then we keep adding x, right? We iteratively keep adding the variables and checking for the significance of these variables. Backward elimination, or we also call it as backward selection, is reverse. We develop the full model and then we keep removing. We develop full model, sorry, not here, here. We develop full model and keep removing the variables, right? Now, stepwise, as I said, is combination of both. Stepwise selection is combination of both, right? We start again with 0, just like what we do for forward selection, right? And we keep adding, right? Now, when you add another variable, right, there might be cross functionality or cross relations which are affecting these relationships. So in such case, you might remove the first one, whereas here you do not remove that. So that's the 3 feature selections that we have, friends. So just to summarize the theory, AIC is just like adjusted R squared, which is a parameter which penalizes the weightage, the model, when a new variable is getting added. right? And it's kind of a measure of a goodness of fit, right? Now, when you look at AIC, standalone value of AIC does not have any significance. Archaic information criterion does not have any significance if you are looking at the single value. Now we will only use this AIC to decide on which model is better, right? The model which has different set of features. We iteratively, repeatedly try this, and we pick the model which has the least AIC. Of course, it has to satisfy the model requirements. Right, so this is about your summary. Now let's try and look at our code. All right. So I'm basically calling the model here. I'm calling the data set. We have cars data set. Now always remember, whenever you have any data set given to you for prediction, we will have to try and first do EDA. Exploratory data analysis is mandatory. Okay, preliminary analysis is mandatory. This would basically give better idea on your data. Right? I have 81 observations and 5 columns. 81 rows and 5 columns. Yeah. Now, you're attaching this data. As I said, EDA is mandatory. We're assuming that we have done EDA. Okay, we're assuming that we've already done EDA. We proceed further. When I say EDA, it's about measuring the first movement, second movement, third movement, right? All these things. And we also have to measure the or visualize the data, right? So when you visualize the data, it gives you more clarity on what we are trying to do there. Okay, so that's the expectation as soon as any data set is provided to you. Right, now next is we try and do summary. Summary is like a one-line command which talks about data. A lot of the entire distribution of the data is speaking here, right? Yeah. So we have horsepower, then we have mileage, right? Volume, top speed, weight. These are the 5 columns. Mileage is your output. Miles per gallon is what you have to predict. Provided the horsepower of the vehicle, volume of the vehicle, top speed and weight. If you have already attended the sessions of 360 Digit and G, then you already know about this data set. And we clearly can see that there are collinear pairs, right? Of course, we'll try and do scatter diagram. This is the scatter diagram which talks about the relation between input and output. Volume is another input variable. We are trying to verify the relation between input and output. But rather than trying out these individual scatter diagrams, in R we have pairs. And this is your pairs command, which basically gives us a relationship between set of input variables, right? Input and output variable in a single diagram, right? This is pairs. And then we have plot also, which is same result. Either you do pairs or plot, but plot of cars, where cars is your data set, right? It's a data frame. Multiple columns are there. Then we have correlation. This is the interpretation, right? Graphical representation, by looking at which we basically take a call on the correlations, right? Next we have collinearity problem in this particular data set, right? We can see volume and weight are correlated. Horsepower and top speed are also correlated, very strongly correlated. And we quantify this using our correlation values. CVOR. Now, rather than typing individual x comma y, even for correlations, we can directly do correlations of the data set. Right? When you do correlation of the data set, we get this particular string. Right? Just like what you're seeing here in the diagram, we get the correlation values here for the same page. Either you refer to the upper triangle or the lower triangle, the values are same. And we have identified that horsepower and top speed, these two values are correlated. Similarly, we are looking at volume and weight are correlated, right? Now, if I proceed with this model, I will see that the coefficients are insignificant, right? They are becoming insignificant. Now, when you have these kind of insignificant variables, right, we can proceed further and try and eliminate the influential observation, right? This influence index plots will give you the influential observations, okay? And when we execute it, we get the visualizations like this, two different visualizations. And we can identify in both the visualizations that record number 77 is like an outlier, influential observation. So we can remove that particular observation and develop the model. This is something that we have already learned, right? Now, when you do that and you try and see here, you still have the collinearity pair being insignificant. And in R, we have the VIF function, which basically talks about this collinearity. And you can see among all, weight has the highest correlated value, right? Now, if I try and develop, I mean, you have to do so many things to decide what is the best feature set among the four variables that you have, right? So we are trying out by looking at by developing the model, then verifying whether everything is fine or not by checking the p values, and we observe that the p values are insignificant for weight and volume, right? And we're trying to investigate on what could be the reasons, right? And as part of this, we did influential variables, influential observations as well. We verified that those as well. But removal of these influential observation also did not solve the problem, right? So there is no other option. Rather, we need to eliminate one of the column, right? Feature selection is what we are trying to do here. Now, before that, manually, you can try and do this VIF, which captures the collinearity between the variables. VIF is calculated using these logics. So we develop a linear model among the input pairs, and we capture the R squared value from that, right? And the VIF formula is basically talking about how strongly the value input variable X is correlated with the rest of the variables. How strongly it is correlated with the rest of the variables, right? So here, X1 is correlated with X2, X3, X4, and we get R squared value here, right? Now this R squared is considered for developing the for calculating the VIF, right? And the VIF value is 1 by 1 minus R squared. This is VIF for that particular x1. Okay, similarly we do the equations for x2, for x3, for x4. Okay, we do the calculations for all these. And then we have AV plots. This is another technique wherein you check the correlations, the relation between y and x in that entire equation. Added variable plots basically talk about visual representation of the relationship. You can see here, it's speaking about how your input variable is affecting output. The blue line is almost like a straight line. That means you keep changing x, your y is affecting very little. Horsepower, you can see there is a big effect. Top speed also is there, there is a good effect. But if you observe weight, literally there is no effect at all. It's almost a straight line, straighter than this visualization, right? So by looking at this, we can say that weight is the variable which is impacting the least, right? This is the variable which is impacting the least. So we stopped, I mean, we basically identify weight to be eliminated, right? So we are checking VIF to verify the collinearity, and we observe that weight is strongly, very strongly related to other variables. That means it is displaying collinearity effect. Similarly, we have added variable plots. Now this added variable plots is basically looking at the effect of that y on x, right? So these are the two cases, and we can develop the model by eliminating that weight. And if you do this and check, you can see the variables are right now statistically significant, right? And you can also verify your R squared value. You can verify the AV plots, and each of that input variable that we are using here in y, in predicting y, are equally, I mean, they're contributing, right? Similarly, VIF we can check, and yeah, VIF you can see that the values are less. Though the thumb rule says if a value is less than, greater than 10, that means there is a collinearity between the pairs. And we have observed that in the scatter diagram, that horsepower and top speed were also having correlation. That's exactly what it is displaying there, but it's not that strong. And because of that, you can see the coefficients are significant itself. They did not become insignificant. So we can keep them in the model, right? And we do model evaluation techniques. Now this is the approach that we take for developing a regression model, and this is a manual approach, right? Now what we discussed is the subset feature selection, and we discussed about these stepwise, or you can say best subset selection. Then we have forward feature selection, and we also have backward stepwise selection or backward elimination. Now what I do here is I install a package called Leaps. Install Leaps, right? And you can say regression subsets, right? You can say regression subsets, or you can do question mark of this REG subsets. Functions to functions used for model selection. Model selection by exhaustive search, forward, backward, or sequential replacement. That is your stepwise. Right? So these are the options that you can pass here for subset selection. I will just apply this. I'm taking mileage and passing all the input columns from the data set. And we have an argument called NV max. Now, NV max basically means maximum size of subsets to examine. So when you're trying to do maximum, you're going to take 15 subset values. So when you say subset, you might look at this. You're developing Y with X. This is a regression model between this pair. Then you say Y, X and X square, polynomial model. X, X square, X cube. So on and so forth, we can keep trying unless, let's say this is insignificant, so we stop at X square. Then we take X1, X1 square, then X2. Right? So we keep on repeating this, and maximum that we can take is 15. Right? That's defined here, predefined. You can design that. So we have developed this model, and if you say summary of this model, yeah, this is the summary, and the one subsets of each up to 4. You are taking this and look at that. First model it has taken this, second model 2, third model 3, fourth model all the 4. Right? One subsets of each size up to 4 selection algorithm. We did exhaustive algorithm. This is by default considered, and we are looking at adjusted R-squared values now. For that model, we are reading the adjusted R-squared values. And you can see this has the highest value, right? Which max? This R-squared is the best among the 4 models that we developed. R-squared is the best for the third model, which do not have weight. Right? You can clearly say weight is not considered. So you're taking coefficients of the third model. So this is your equation. Right? So this is one approach that you can take. And here I'm applying forward feature selection. Same function. You're passing the parameter method is equals to forward, and that's exactly what we have done here. It's only forward feature, it's not exhaustive. Right? You can clearly see that weight is not chosen. Then we will do the partitioning, and we develop the model without weight, and we get the equation. Right? And we'll try to predict the values, measure the error. So we will verify on the test data, see how well this equation that we got is working. Right? How well it is working on this model. Right? That's what we are trying to understand. And yeah, once we calculate the error, we are measuring RMSE. So it is 4.29 on test data set. So we are trying to see what would be the error on training data set. Very, very similar. So nothing to worry. It's not overfit case, both are same. Now you can also try and apply step AIC. Now this is another approach, friends. There is an inbuilt function called step AIC in R, which would basically do the same task that we have just done by looking at the values. So it's first doing forward. Remember, it is taking the full model, backward elimination. It is taking full model and developing the regression model and sees that this is the intercept and these are your other weights, other coefficients. And here it is looking at the AIC values. Yep. So we are removing AIC values right here. The value which has the least AIC, basically. Right? And yeah, this has the least AIC weight. So you remove that weight and then see. So what is happening here? This is the model, and you get this model. Right? Among these two, if you see, AIC value which is less is considered to be the better model. The overall model is AIC, right? The model which has least AIC is considered to be the better model. Right? So this is basically how we look into the models. Yeah. And this is the equation that we get finally. Right? So it is automatically calculating what is the equation by considering the best model among all. So iteratively it is doing that and capturing this best model. Right, so these are your step AIC functions. And you can do a step question mark of step AIC and read about that. Choose a model by AIC in a stepwise algorithm. And yeah, these are the two things that you can pass: backward, both, or forward. That's your direction. Model selections, right? Mode of stepwise search. All right, so that's about your step AIC concept, which basically used for choosing the best model by choosing the features which gives us the best result. Now, when we say best, one thing we need to remember, right? It does not, maybe it doesn't give you a better performance, right? But it is simplifying by removing, by eliminating unwanted features, right? The complexity of the model is getting reduced, right? So that's your yeah. Step AIC functions. And any questions, friends? Okay. Let's see if we have any questions. Not really. Not really. It doesn't look at VIF. It's nothing to do with VIF. It's a different parameter altogether. Mathematically, there is a calculation. It looks into the weightages and all that. Yeah. Okay, thank you. All right. If no more questions, no further questions, then we can wrap up the session. Sure, Sheikh. Yep, yep. That's the idea, Sheikh. Yes. All right, friends. Glad you're appreciating the effort, and I'm glad that it is really helping you. So let's connect again in the next webinar with another topic. And until then, please keep safe. And thank you so much, and good evening, friends. Yeah, it's just a step AIC function. I don't know. You can probably look into the YouTube video and type it. This code is already there with you. It's just this particular last couple of lines is what you have to apply. Two functions. One is step AIC function. The other one that you have to look at is this function, right? Regression subsets. You can try that. Yes. All right, friends. Thank you and good evening.